Yeah, so in this example, at the end of last hour, I mentioned this theorem that makes it very easy to calculate a residue when the function you're dealing with is of the form, a function that's nice and analytic at A, f, divided by a function that has a simple zero at A. Those come up a lot in practice, as you'll see when you read Stein, where he does examples of applications of the residue theorem. You could always say residue of a function h when h has a pole at A. That's what we know. And eventually we'll be able to do the residue even if h has an essential singularity at A. But of course, if h is analytic near A, then the residue would be 0. Okay, so I thought I would do the proof real quick of this. So G is assumed to have a simple 0, meaning G of A is 0 and G prime of A is not 0. Then that means I can, when I expand G in a power series about A, all these calculations involve playing games with power series about the point A. Well, when I write out the power series, the A0, A0 term is 0, because G of A is 0, and the A1 term is G prime of A, that's not 0. So I realize this is a simple 0, and I can factor out a Z minus A from the power series and get an analytic function given by a power series with the same radius of convergence as the one for little g. I'll call that big G. And the constant term on that thing is A1. So in particular, notice that G of A is equal to A1, and A1 is equal to G prime of A. So we just see that from power series. I'll use that in a second. Okay, so now when I write the function f over g, I'll put that z minus a in front times capital G in the denominator and realize, aha, I can factor out a z minus a. And that's exactly what you want to get to find the principal part near a. You want to find those terms that do the blowing up. Okay, and so what's left is f of z over capital G of z, which is nice and analytic near a because G of a is not 0. Okay, so it has a regular power series, A0, capital A0 plus capital A1 times z minus a plus etc. And when I distribute that 1 over z minus a through, I see the residue term. It would be the A0 over z minus a, and the rest of the stuff is a regular power series with radius of convergence something positive. And so we can read off from this right here that this is the residue. Period. And so we see that the residue, let's see, that's the A0 term. And the A0 term is equal to A0, f over g, is equal to A0. And that's the value of that function inside the square brackets at A. So that would be f of A, that's equal to f of A over g of A. And g of A, here, we use this in this formula right here. G of A is equal to G prime of A. So check. That's the proof. It's a standard problem to sort of redo this from the next obvious question is if I had f over g, where f is similar, is analytic as before, but now g has a double 0 at A. So that would mean that g of A is 0, g prime of A is 0, but g double prime of A is not 0. That's a double 0. then you repeat that and find yourself a formula for the residue f over g, which that situation comes up enough that that's a worthwhile thing to go through. That's been an exam question, a qualifier question, so it's something a good idea to sit down and do. Someday it might even be a homework question. Questions about anything? Oh, let's see. So back to that calculation. At the end of last hour, I was calculating an integral. If I use my new improved formula, I have to calculate the residue at e to the I pi over 4 and e to the I 3 pi over 4 of 1 over z to the 4th plus 1. And there the numerator would just be the function 1, and the denominator would be 4 times z to the 4th plus 1. And when I calculate f of a over g prime of a, of course the f of a would be 1, but g prime would be 4z cubed. And of course that's not 0. G of the point is 0, but g prime is that 4 e to the I 3 pi over 1 over 4 e to the I pi over 4 to the third power. That's not 0. Okay, so I can mess around with that and clean it up and get, let's see, I'll pull the 4 out front. That would give me a pi over 2 times I. And here I would get 1 over e to the I pi over 4 cubed would be e to the minus I 3 pi over 4. And let's see, this other one would be e to the minus 9 pi over 4. Minus I 9 pi over 4. And you realize those are just complex numbers. This one is, let's see, what is it? That's minus square root of 2 over 2 plus I times the square root of 2 over 2. This one's square root of 2 over 2, because I go all the way around, that would give me plus pi over 4 when I go all the way around 2 pi plus pi over 4 more. So that's, let's see, where is that? It's minus pi over. So I would go around pi over minus pi over 2, and then I'd be 1 more pi over 4. That would be minus square root of 2 over 2i. Anyway, you plug those in, and you get something very simple. This turns out to be equal to pi over the square root of 2. Questions about that? That is one of those functions that's very it's difficult to find an antiderivative for it. If you work really hard, you can find one and name it something, but it's a major mess. So this is a greatly improved way to find that number if you just want the integral from minus infinity to plus infinity. Questions about that one? Yeah.
Yeah, sorry, shouldn't it be minus I root 2 over 2 for the first one?
Oh, really? Let's see. No. Minus 3 pi over 4. You're right. Thank you. Right, sorry. Oh, yeah. Sorry, I didn't have my nose in my notes. Answer's still correct, though. Let's see, here's another exciting application of these ideas. It's very important to find the actual Fourier transform of certain famous functions. And Stein is crazy about the Fourier transform, you'll notice. He has chapters on it in all his books, basically. And the Fourier transform is you take a function on the real line and you get a new function called f hat of s, which is the integral from minus infinity to infinity, e to the I s x f of x dx. So give me a function on the real line, usually an L1 or an L2, and this spits out a function of S, a new function called the Fourier transform. And the mind-blowing thing is, well, the best place to define Fourier transform is L2, because it's an isometry of L2, basically, depending on where you put your 2 pi's. And a fascinating thing about the Fourier transform is it turns differentiation into multiplication by S. So it turns differential equations into algebraic equations, which is a great thing, because then you take the Fourier transform of a linear equation, it turns it into an algebra equation. If you solve for the Fourier transform, then you can undo the Fourier transform and get the solution to the differential equation. That's a mind-blowing tool and extremely useful in partial differential equations and even ODEs. And the mind-blowing thing about the Fourier transform is it's basically its own inverse. The inverse Fourier transform is the same formula with a minus e to the minus isx in it. And maybe it depends on where you put your square root of 2 pi's, but there'd be square root of 2 pi's floating around in the formulas, depending on what your favorite way of doing it is. But basically, the Fourier transform is its own inverse. So first you hit a differential equation with it, turn it into an algebra problem, and then you solve for the function f hat. Then you undo the Fourier transform basically by doing it again. And so it's a fantastic tool. And so let's see. I want to do an application here of calculating the Fourier transform of. Let's do f of x equals 1 over x squared plus 1. That's kind of a famous one. And the key to doing this, and using the residue theorem to do it, is that e to the ISZ let's calculate that. That's equal to e to the IS x plus IY. And that would be, let's see, e to the I times I is, so I get a minus sy, and then the rest would be an e to the ISX, which has modulus 1. And so the interesting thing is that the modulus of e to the ISZ is equal to e to the minus sy, because the modulus of this term is 1. And so the fantastic thing for us is that this is less than 1 if s is bigger than 0 and y is bigger than 0. In other words, in the upper half plane. It's also less than 1 if s is less than 0 and y is less than 0. That's the lower half plane. Okay, so there's going to be 2 cases to consider. Let's first do the case S positive. It can be greater than or equal to 0, maybe, because the 0 case is and very easy. You can use freshman calculus to do the case equals 0. So maybe I should say that. The case S equals 0. Integral from minus infinity to infinity of 1 over x squared plus 1 dx is the limit of arctangent, limit as r goes to infinity, of inverse tangent x between minus r and r. That's pi over 2 minus pi over 2, and that's pi. So that's kind of a dumb case, don't need anything fancy. But now I'm going to do the case S positive. Then the key here is that e to the ISX SZ is less than or equal to 1 on the upper half plane. And that's the key to making this work. So when I do my toy domain, the kind of the knee-jerk one to do is this one. Have a circular part here. Go from minus r to plus r. Then the integral along the realigned part is the part we want. We'll call this gamma. And we're going to take f of z to be equal to e to the I sz divided by z squared plus 1. That has a single spot where there's a singularity, namely at I, where the denominator vanishes. And so the integral, the key is that the integral along c sub r tends to 0. That would be less than or equal to the max of e to the ISZ, which is 1. That's max is going to be less than or equal to 1. Oh, let's see. I need to figure out what's the, well, I'll think about it in a second. Z squared plus 1 on c sub r times the length of c sub r, which is pi r, not 2 pi r. It's half a circle. Okay. And let's see the, I like to use the denominator estimate. So note, e to the ISZ is less than or equal to 1 on c sub r. And let's see, I want to use z squared plus 1 is, I need to use a greater than or equal to. That's the denominator inequality I keep talking about. And let's see, if r is bigger than 1, this thing here would be equal to r squared minus 1 when r, this is equal to r squared minus 1, when r is bigger than 1. Okay, so e to the ISZ over z squared plus 1 would be less than or equal to 1 over r squared minus 1 on c sub r when r is bigger than 1. Okay. When people on exams put an r squared plus 1 in the denominator, of course they lose points because that's an incorrect inequality. If you don't want to mess around being careful about doing that denominator estimate, you could always use the basic polynomial estimate. So remark, or use, let's see, a z squared is less than or equal to z squared plus 1 is less than or equal to a z squared. And of course this would be the basic polynomial estimate that you would need. And this would be for r bigger than something. Then you wouldn't have to be careful with that minus 1. And it's maybe less to think about. Questions about that? So let's call it. So we conclude now that the integral around the circular part is less than or equal to 1 over r squared minus 1 times pi r. And that goes to 0 as r goes to infinity. And that's important. That means we conclude, let's see, this is the integral along gamma would be equal to the integral along the real line part plus the integral around the circular part. I don't think I called this part down here would be the real line part. I guess maybe I should call this gamma sub r to be picky. And so by the residue theorem, this would be 2 pi I times the residue at I. And now we do have a quotient, e to the I s z on top, and the bottom is it's simple 0 at I. So here now we, like before, this is the f of z, and this thing is the g of z. And so as we let r go to 0, not go to 0, go to infinity, then this would tend to the integral we want, which would be the Fourier transform, f hat of s. This one tends to 0, and this one is 2 pi I. F of on top would be e to the I s times I. And on the bottom, we get the derivative would be, let's see, g prime of z is 2z, which is not 0 at I. And so this would be 2 times I. The i's cancel, and I'm left with something real. I get, and the 2's cancel. It's pi e to the minus s. So the Fourier transform tends to 0 rapidly at infinity, as you go to positive infinity. The case, question about that? It's kind of a fun thing to do. And that comes up in PDE when you actually want to use that transform. The next case would be S negative. Then you run into this difficulty that e to the isxz rather is not bounded in the upper. So e to the sz, in fact, is terrible. Is not bounded on the upper half plane. In fact, it's a real mess. So that would bomb if you tried to do it that way. In fact, it's a mess. It's terrible. It blows up just like an essential singularity. But it is bounded on the lower half plane. But now it is bounded by 1 on the lower half plane. Okay, so now we're going to use the lower half plane toy region. Let's see, what should we do? Oh, I want to integrate from minus r to plus r. So this time I'm going to take I sub r going this way, and I'll take my C sub r going that way, and I'll call this gamma sub r. And then there's exactly one singularity at minus I. And notice that that's clockwise. That changes the residue theorem. So the clockwise residue theorem is that the integral around gamma sub r of f of z dz is minus 2 pi I. Because it's going the other way. And when you go the other way, you get a minus. So it's minus 2 pi I times the residue at minus I of e to the I. S is negative now. Z over z squared plus 1. And so in the limit, that's going to go to the Fourier transform for negative s. And that's going to be equal to minus 2 pi I e to the I s times minus I over 2 times minus I. Funny, the minuses cancel, and I'm left with, the 2's cancel, and I'm left with pi times e to the minus s. So it's e to the plus s. And of course, s is negative, so that still goes to infinity as s heads out to minus infinity. So if I were to graph f hat of s now, it would look like this. It would be exponentially decaying out going this way, and exponential decaying symmetrically going out this way, and this would be pi when s is equal to 0. And it's e to the minus, it's pi times e to the minus s out here, and it's pi times e to the plus s on the left-hand side. Questions about that? Let's see. Well, now I want to do a very famous example. It's in all the books. Let's do this integral comes up in optics and in interference of waves that go through parallel slits. So it's kind of an important integral. Of course, they could compute it numerically if they wanted, but the amazing thing is this integral is exactly pi. And that's a famous integral. That's a conditionally convergent integral. And if you graph this function, the sine wave, let's see, sine t over t doesn't blow up at the origin, so it's, in fact, it tends to 1 at the origin. And then you get this beautiful decaying bumps. And it's symmetric about the y-axis. And the interesting thing is these bumps, that's a negative bump, this is a positive bump, the areas are getting smaller and smaller. So the alternating series test shows you that that integral converges. But if you add up the positive area of all those bumps, it goes to infinity. So that in freshman calculus, you can see that this integral is conditionally convergent. They call that. And there you use the alternating series test because those bumps are they're easy to estimate those bumps, and you see they get smaller and smaller. So it's conditionally convergent, but not absolutely convergent. Which is a stronger kind of convergence. The sum of the positive areas, in fact, is infinite. Okay, but I can show you how we're going to calculate this thing. So the first try you would naturally do, you would take maybe, let's see, I want to do, let me get this out of the way. I want to do this contour, another one of those standard contours. I need to take a little bite out near the origin. So I'll call this C sub r. It's going counterclockwise. I like to make this one called C sub minus C sub epsilon. So C sub epsilon would also go counterclockwise. So minus c sub epsilon is the clockwise version. And this goes from minus r to minus epsilon to plus epsilon to plus r. And the origin is right here. And you would think, okay, if I'm going to calculate that integral, I should try f of z equals sine of z over z. But you maybe remember seeing the graph of cosine of z. Well, this graph of cosine of z is just shifted by pi over 2. So it's terrible in the upper half plane. So that's going to bomb. So the ouch is sine of z is terrible on the upper half plane. It's also terrible on the lower half plane. It's just terrible. Okay, so that's not going to work. And so your second try, the second try would be f of z equals e to the iz over z. And that's going to get us somewhere. Maybe it's not so clear in the beginning. You'll see why it's related to the integrals I want to get. Let's call this left-hand side L1 and this right-hand side L2. Okay, let's think about if I integrate along the left side plus the integral around the right side of e to the iz over z dz, that would be the integral from minus r to minus epsilon plus the integral from epsilon to r, and then I would have e to the it over t. And e to the it is cosine t plus I sine t. So this would be cosine t over t plus I sine t over t dt. So that's e to the it over t. And you look at that for a second and realize, let's see, cosine is even and t is odd. So this one is odd. And this one, sine t is odd and t is odd, so this thing is even. And so the left-hand integral cancels the right-hand integral when the function is odd. So that's going to spit out nothing. But when it's even, then you get 2 times. So what this is going to be equal to 2 times the integral from epsilon to r of sine t over t. And there's an I there in front of that thing, because that's an even function. Okay, that's the integral we want. Of course, I'm going to let epsilon go to 0 and r go to infinity. Okay, now I need to, my next claim, we're going to want that. So my next claim is that the integral along the outer circle of f of z dz tends to 0 as r goes to infinity. And this is a spot I've kind of warned you in the past. This is like that problem in the homework where the basic estimate fails us. So the basic estimate fails us. So the integral around c sub r, let's see, that would be less than or equal to the max of e to the iz over z on C sub r times the length of the half circle, that's pi r. And this max is 1 over r. It happens at z equals r. That happens at z equals r on C. Plus or minus r2, so both ends have that problem. And so I get 1 over r times pi r, that's pi. That doesn't go to 0. So we get less than or equal to pi, and that doesn't go to 0. So darn. Let's see, it doesn't go to 0. Okay, so we have to be more careful, and this is an example where we have to write out the integral. So the integral along C sub r of e to the I z over z. Let's see, I should parameterize C sub r like I always do. C sub r is parameterized by z of t equals r e to the I t, as t ranges from 0 to just pi. So the integral along C sub r of e to the I z over z dz would be the integral from 0 to pi. Let's see, I'd have a r e to the I t on the bottom, and at the top I would have an e I r to the I guess I'll write e to the r I t, and then r z prime is I r e to the I t dt. Okay, what's that? Now I'm going to take the modulus. So I'll put a modulus outside. And this isn't the basic, this is one of the integral estimates. What did I call it? Basic estimate number 1. It's more primitive than when you do it for contour integrals. Basic integral estimate number 1 back in the early days of thinking about this. I can take the modulus inside. So this would be less than or equal to the integral from 0 to pi. Let me take the modulus of e to the r. Let's see, r e to the I t is r cosine t plus I r sine t. And the modulus of the denominator is just going to be r, because the modulus of e to the I t is 1. And here I get the modulus of I, which is 1. I'd get an r, and the modulus of e to the I t is 1 dt. So here I'm using that this is less than or equal to the integral of the the modulus. Well, let's see that e to the, so this thing on the top, let's see, so I get less, that's, let me mess around with this. This one is r. That cancels that r on the top. This one is 1. And so this is equal to the integral from 0 to pi. I get modulus of e to the I r cosine t. That's 1, because e to the I something is on the unit circle. And then the other one is the modulus of e to the I times I is minus r sine t dt. This one is 1. And this one, of course, being real, is just e to the minus r sine t. And so, after that careful calculation, without doing any primitive, I'm not losing anything really, or at least not as much as I did with the basic estimate. What I get is that the integral around the outer circular part is less than or equal to integral from pi e to the minus r sine t dt. And this is a famous integral that Jordan analyzed way back. I'm going to estimate this. This is going to go to 0 as r goes to infinity via, it's called Jordan's lemma. It's just a way of using basic calculus to estimate that integral. So let me draw a graph of what it looks like. Let's see, here's the y-axis, here's t-axis. I'll go from 0 to pi, and pi over 2 is in the middle. Let's see, sine of t I'll do in blue. It's 0 here, it's 1 at pi over 2, and then it goes down and is 0. Okay, so this is sine of t. And if I multiply that by minus r, I get a curve that goes way down like that. This is minus r sine of t. And so when I take e to that, e to the 0 is 1. So this is 1 right here. Peak's right there. Looks like 1 is a little bit higher up. There's 1. Okay, so it's 0 right there, but then e to the minus r sine t gets big and negative real fast. So it's going to go down and be small for a long time and get really small, in fact, and then go back up to 1 at this other end. And of course, the area under that's going to be small. So I could estimate it by really primitive means. I could take a little rectangle. Let's see. In this big part in the middle, I could make it uniformly small. So it'd be less than epsilon times the width of 2 pi. And then I take a little tiny rectangle here, and it's bounded by 1 there, times some small base. I can make small rectangles that hold this area. And that would be a very primitive thing to do. And it would be a perfectly good proof. So I could do it by a baby method. The baby method, I would take, here's 1, here's 0, here's pi. That thing is very steep, goes down to 0 and stays small. And so what I would do is take a box that contains this stuff out to here, show that that's small, and then take a narrow skinny box here and show that that's small. And that would contain the area. So the orange boxes that would be slightly greater than the area under of e to the minus r sine t dt. And it would be pretty easy to show that you can make those area, the orange boxes, go to 0. Okay. Well, here's Jordan's method. Let's see. I'm going to take this line here. So I'm going to take this line here. Sine is convex down. And so sine is strictly less than that purple line. Let's see, that's 2t over pi. Is that purple line. And sine of t is less than it. Okay. And it's symmetric about pi over 2. Okay, so there's my picture. We have 2t over pi, 0 is less than or equal to that, is less than or equal to sine t on 0 to pi over 2. Okay, so when I take minus r times that, I would get minus r sine t is less than or equal to minus r 2rt over pi is less than or equal to 1. I mean 0. On that same interval. And the exponential is strictly increasing. So, and e to the minus rt, what? E to the minus r sine t is less than or equal to e to the minus 2rt over pi is less than or equal to 1 on 0 pi over 2. And now I can get somewhere. Let's see, this is exponentials are always positive. So this is a positive thing. And so the aha moment is gave Jordan enough to estimate. So now, let's say the integral from minus pi, 0 to pi, by symmetry of e to the minus r sine t dt equals 2 times the integral from 0 to pi over 2, because it's by symmetry. So here, this is strictly symmetry. And that's going to be less than an integral that's easy to calculate. So that's less than, it's actually strictly less than, integral from 0 to pi over 2 of a freshman calculus integral, e to the minus rt over pi dt. And you do a freshman calculus calculation, and you get that this is equal to 2 times, let's see, the antiderivative is minus pi over 2r, e to the minus 2r over pi t, evaluated between 0 and pi over 2. Which is pi over r times 1 minus e to the minus r. And that's 1 minus something that's between 0 and 1. So that is less than pi over r. And that's so hooray. Yay. That goes to 0 as r goes to infinity. So that's the battle. Once you have that, the rest is going to fall through. I don't have time to finish this in the last minute, but next time we use the pole, simple pole. By the way, the simple pole of e to the I z over z at z equals 0 to show that the integral along this little minus c sub epsilon e to the I z over z is going to tend to something specific, and it's going to be pi basically. minus pi I.